We begin Calc BC with a brief review of limits that will take us about 2 weeks, and they'll cover limits and continuity and just refresh your memory on the different strategies that you used last year in pre-calc honors. So for this video, we're going to start with evaluating limits analytically. So if you can open up your notebook or grab a sheet of paper, this is part 1, evaluating limits analytically. So we'll take a look at a few examples, beginning with problem 1, where we're looking at the limit as x approaches 2 of the function -2, and how do we, or what strategies did we use last year to determine a problem like this? So one strategy that might come to mind is just, if that is my function y equals -2, and I graph y equals -2 on an xy axis, y equals -2 is the horizontal line. So this is y equals -2. And let's go ahead and extend the graph a little bit further out. Oh, it's a little bit messy here. Okay, so here's our graph y equals -2. This question is asking what is happening, or what value are we approaching as x approaches the value of 2. So we want to look at this as x equals 2 is right here. So in this direction, as we approach from the left and as we approach from the right, it appears that we are approaching a y value of -2. So -2 is the limit, because as we get closer and closer from the left and from the right, we come to the same y value of -2. And I usually just pick up my fingers the way that the highlighter, and even putting the highlighter over from the left and right of the function, we see we meet at a point, and it's the intended height that is the idea graphically of a limit. So that value must be the same from the left and from the right. Problem number 2, we're going to take a look at limit as x approaches -1 of x squared minus x minus 2 over x plus 1. So you might remember that for as opposed to problem 1, where you can't simplify -2 the function any further, for problem number 2, you can simplify the top trinomial by factoring that. If you were to factor that either using the different strategies you learned in the previous classes, like X method, box method, however you learn to factor x squared minus x minus 2, you're going to use that and get that my two factors are x minus 2 and x plus 1 over the binomial x plus 1. Then we simplify our expression for f of x further by canceling out the common factor on top and bottom. And then we're left with the limit as x approaches -1 of just x minus 2. And if you remember, the strategy with this is simplify the function as much as you can, canceling out common factors, and then re-substitute back into the resulting expression that's left over. So as x approaches -1, the limit as x approaches -1 of x minus 2 would be direct substitution of -1 into x would give us -3. And for 3, here's a challenge problem. So limit as x approaches -3 of blank. I'm going to say blank here because I want you guys to see if you can pull out from your memory what this function is. And it looks kind of funny with the double brackets there, but it was a special type of function that you did seen in either Algebra 2 Trig or pre-calc honors. So if anyone said greatest integer function or step function, you got it correct. So we're going to go ahead and use our knowledge of what this function is in order to come up with the limit as x approaches that integer value of -3. So it's called a step function because any number that you plug into that function, so let's kind of talk about this function in case you haven't seen it before in your previous classes or you don't remember at all. What happens when you plug in, so let's say this is my greatest integer function. If I was asked to substitute in 2.2, I call this function informally the round down function. And the reason is that you round the value that you plug in down to the nearest integer. So that would give us 2. So if I were to plug in, let's say, what is the greatest integer of 3.9, you might be tempted to say it's 4 because we're used to rounding using traditional rules, but this is the round down function, so the nearest integer would be 3. So graphically, if I think about, well, how is this going to play out in terms of what the function looks like on an XY scale? So let's think about, let's say if I were to plug in 0, I'd get 0. If I were to plug in 0.1, rounding down to the nearest integer would still get me 0. 0.5 would still be 0. 0.9 would still be 0. All the way up, really, 0.99, the closer and closer we get to 2, but just right before 1, we'd still be rounding down to 0. So scratch the 2, I meant 1. So what happens then if we get to 1? Well, we get to 1, now we round down to 1. So now at this point, we're rounding down to 1. So what we do is we say at 1, there's an open circle, or it's undefined at that open circle, but defined for the function at 1. If I plug in 1.1, I get 1, 1.3, 1.9, all of that rounds down to 1. So we get the second step of the function, and that goes all the way up to 2, where that's undefined, but then defined at 2, the y value of 2 for 2, and then so on and so forth. So we continue this trend in all directions. And this is our step function. So when we're asked, what is the limit as x approaches -3, we're going to go, let's go actually extend our graph out to -3 a little bit further. So let's see, what happens when we approach -3? So with my highlighter, I'm going to look at the limit as it approaches from the right, -3 from the right. And remember, we're approaching the x value. And then also from the left, and we see that our fingers don't meet, or the arrows don't meet at a common point. So here the left-hand limit is different from the right-hand limit, so in which case we say the limit does not exist, or DNE, so does not exist. And then finally, for part 1, we're going to look at what happens when we have a rational function. So for question number 4, we'll look at what happens when the limit of the function 1 over x plus 1 minus 1/2 all over x minus 1 as x approaches 1. So remember, if the function itself can be simplified algebraically, we go ahead and simplify that algebraically. You can see that we have a function that is a complex fraction, where we have a fraction within a fraction. So what we're going to do is get rid of our fraction within a fraction by combining. Let's first combine the top two functions. So let's work on that numerator and combine those together. So I want you to go ahead and hit pause on the video and see if you can work out this problem. I'll show the solution to it and work it out after you've had a chance to enter in the answer and do your best to simplify that fraction. So remember, the strategies always are simplify and then resubstitute back in once you've simplified algebraically. Okay, so the common denominator of these the denominator of your numerator is 2 times x plus 1. So the left-hand fraction is missing the 2. So you have 2 over x plus 1. So our common denominator is 2 times x plus 1, or x plus 1 times 2. The left fraction is missing the 2. The right fraction is missing the x plus 1. So minus x plus 1. All over our common denominator of 2 times x plus 1. And that's all over your denominator of x minus 1. Then we go further and we simplify the top of our numerator. And we get 2 minus x plus 1 with the negative distributed is minus 1. So 2 minus 1 is 1. And then you have 1 minus x all over 2 times x plus 1. And so we still have it as a complex fraction all over x minus 1. If you remember simplifying fractions as keep, change, flip, you keep the top, which we have now as simplified 1 minus x over 2 times x plus 1. You change the division to multiplication, and then you flip the denominator. So that instead of x minus 1 over 1, you have 1 over x minus 1. And so you see on here, I'll highlight, you notice that the factor on top and bottom of now your simple fraction can be simplified by canceling those two out. If you remember, to flip or to factor out a -1 would then allow those two factors to be the same. So if I factor out a -1, I can cancel these. And so my simplified function that I'm trying to find the limit of now is -1 over 2 times x plus 1. And so if I do direct substitution at this point, I end up with -1/4 is the limit.